In the previous video, we looked at how we could use Kirchhoff's laws to analyze mathematically the behavior of an RC circuit. In this video, we will see how, even without doing the full analysis, we can determine the behavior of the RC circuit in certain limits, in the limits of very early time and very late times. First, we start with a recap of the general results that we had derived using Kirchhoff's laws. For a charging capacitor that starts out uncharged, and then a switch is closed and it starts to charge, what we found was that the charge follows a time dependence given by this sort of function, where Q final is the final asymptotic value of the charge that the capacitor tends towards, and tau is the charging time constant with units of seconds, which will be equal to R effective times C effective for the relevant charging circuit. And we know that if we were to plot this graph, that it would look something like this, asymptotically tending towards this value of Q final. One thing to note is that when t is equal to tau, you get Q is equal to Q final times 1 minus e to the minus 1. So this number e to the minus 1 appears fairly frequently, and so it's good to know its approximate value. So e to the minus 1 is approximately 0.37. And so this tells us that if you weight one time constant, then your Q at t equals tau is going to be 0.63 Q final. That means after one time constant, you will have reached 63% of your final charge. When t is equal to 2 tau, then you get Q is Q final times 1 minus e to the minus 2. And your value then is about 86% of Q final. And so on and so forth. So after 3 tau worth of time, you will have reached 95% of your final charge value. The important features of the graph to note here are that initially it rises very steeply, and then later on the slope here is close to 0, which indicates that the current through the capacitor is close to 0. For a discharging capacitor, we found that Q of t was Q naught, the initial charge, times e to the minus t over tau. Again, tau is the time constant here. It's the discharging time constant, and it would be R effective times C effective for the discharging circuit, which might be different from the charging circuit. Here, if we plot what this graph looks like, we just get a simple exponential decay down to 0, starting at Q naught. And we can see here that when t is equal to tau, Q at t equals tau is 37% of the initial charge. If you weight 2 time constants, then you will get Q naught times e to the minus 2, which is about 13.5% of Q naught, and so on. We tend to summarize these behaviors into the following simple rules. An uncharged capacitor is like plain wire. This is because for capacitors, we have Q is equal to C delta V. So if Q is approximately zero, then that tells you that delta V is approximately zero, which is the behavior you would expect from a plain wire. And so the current flows freely. A fully charged capacitor its behavior can be taken to be, there are two ways that you could describe it. You can think of it as a broken wire, no current. More accurately, perhaps, you can think of it as a battery with variable voltage, right? This is probably the better description because you won't make any mistakes of thinking that because there's no current, there's no voltage. There is definitely a voltage across the capacitor because, again, we have Q is equal to C delta V. So as long as there's charge, there is a potential difference across the capacitor. And this potential difference can drive a current if there is a discharge circuit available, or if we are still in the charging mode, then this voltage will fight against any current that tries to go through and basically stop current that tries to go through. All right, with these simple rules in mind, let us analyze a few RC circuits. So here's one example. So in the circuit below, the switch is initially placed in position B for a long time until the capacitor is fully discharged. The switch is then flipped to the A position. Just after the switch is flipped to A, what is the initial current through the battery? So let us draw the circuit with the switch in position A. And also with the understanding that the capacitor is uncharged. And so capacitor like a plain wire. So with that understanding, what does the circuit look like? It looks just like this. And so we have a 12-volt battery, we have a 3 ohm resistor. We would normally have the capacitor over here in the bottom part of the circuit, but in the limit where the charge is zero, where we've just flipped the switch, so charge hasn't had any time to build up, we can treat the capacitor like a plain wire. So this is what the circuit would look like to the battery. And so then we can say that, oh, well, current is delta V over R. And so this would be 4 amps. All right, we're asked what is the time constant for the charging of the capacitor, and the switch is in position A. Well, let's draw that circuit again. So we have battery, resistor, and capacitor. This is 3 ohms, this is 3 farads, this is 12 volts. And so if we look, there's only current flowing in one loop. And so from there's only one capacitor, the 3 farad, there's only one resistor, the 3 ohms. And from the perspective of the capacitor, that is, if I were to basically cut out the capacitor and treat, that is, if I were to cut out the capacitor and treat this as one node and this is another node, you can see that the resistance that I see going from one node to the other is just 3 ohms. And so we have tau is equal to R effective times C effective. And so that's 3 ohms times 3 farads is going to be 9 seconds is the time constant for the charging of the capacitor. All right, now the question is, after a very long time, the capacitor is fully charged. What is the final charge on the capacitor? Well, we know that Q is equal to C delta V. And we know that a long time afterward, Well, first, let me again draw what the circuit is in position A, with the switch in position A. So we have battery, we have capacitor, we have the resistor. So this is what the circuit looks like for the charging of the capacitor. And what we know is that as time passes, after a very long time passes, there's no current flowing through the capacitor, which means that there's no current flowing anywhere in the circuit, really, in this case, because there is no path starting at the positive end of the battery and running to the negative end that is complete. The capacitor is blocking the only path. So since there's no current, that tells us that there is no voltage drop across the 3 ohm resistor. And so if we gain 12 volts across the battery, we must be losing all 12 volts across the capacitor. And so the delta V for the capacitor is 12 volts. And so we can say Q equals C delta V. C is 3 farads, delta V is 12 volts. And so this gives us 36 coulombs as the charge on the capacitor when it is fully charged. What is the final voltage drop across the capacitor? Well, as mentioned before, we can draw the circuit when the switch is in position A. And we have the battery, the capacitor, and the resistor. And if we do the Kirchhoff loop rule, going around, say, counterclockwise, we would have E minus delta VC, which is the voltage drop across the capacitor, minus IR is equal to 0. However, when t tends to infinity, we know that the current is going to equal 0 or tend towards 0. And so we get simply that delta VC is equal to E in this case, which is equal to the full 12 volts of the battery. Now that the capacitor is fully charged, the switch is now flipped to position B and the capacitor starts discharging. What is the initial current through the 2 ohm resistor? Well, now that we're in the discharge phase, the capacitor is going to act like a battery, but with a variable voltage. What voltage does it start with? We know that for a capacitor, the voltage is determined by the charge, according to Q is equal to C delta V. Now, when we flip the switch, the capacitor will start to discharge, but the charge on the capacitor can't change suddenly. After all, it takes time for the charge to start moving and eventually work its way from the positive plate to the negative plate. So that means that the voltage on the capacitor can't change suddenly either. So to find the voltage just after the switch was flipped, we look at the voltage just before the switch was flipped. And we know that that was 12 volts for the capacitor. So our circuit now that the switch is in position B looks like the capacitor and the 2 ohm resistor. But in particular, we know that just after the switch is flipped, the capacitor is acting like a 12-volt battery. And so this would look like this. And so our current, which is delta V over R, is going to be simply 12 over 2, which would be 6 amps. Of course, it doesn't stay at 6 amps. As the charge on the capacitor decreases, so does the voltage. And as the voltage decreases, so does the current. And finally, we are asked for the time constant for the discharging of the capacitor. Well, the relevant circuit for the discharge is the capacitor and the 2 ohm resistor. This is where the current flows. This will be the positive plate of the capacitor, the negative plate. Current is flowing this way. And so we get tau is equal to R effective times C effective. And this time it is going to be 6 seconds for the time constant. So there you go. There are more complicated examples of RC circuits that we will see in class and on the Friday sessions. But hopefully this video gave you a brief taste of some of the simplifications we can make. Once again, when you have an uncharged capacitor, Since there's no charge, there's no voltage drop, and it acts like a plain wire. When you have a fully charged capacitor, it acts either like a broken wire, not allowing current to pass through, or like a battery with a variable voltage.